Welcome to Maths with EJD. I'm still talking about cooperative game theory. I think this is the fourth video in this series on cooperative game theory under the main series of game theory, right? Of course, we see that cooperative game theory is that it talks about that in a situation where, because of mutual benefits, players come together instead of competing with themselves, they pool resources together so they can get more benefit, they can get more playoffs in the sense of game theory, right? So I've talked about the introduction where we introduced all of that idea generally, and then we looked at the core of a game theory where um, we saw the the payoff that each player should have so that they don't pull off like that situation where if they have to pull off it will be at a loss to them. And then we in the last video we consider the sharply value in cooperative game theory, and that actually talks about the fair way in which the final payoff should be shared depending on the contribution of depending on the value of the participating players. So here we are looking at the last video on this idea of cooperative game theory, except if something else comes up in this area. Of course, it doesn't mean game theory has ended, right? We still continue with other aspects of game theory. But as far as cooperative game theory is concerned, we are looking at bargaining solutions, and let's see what that is about. Okay, I guess I want to switch this up. So yeah, let me go purple, right? Now introduction to bargaining solutions. Okay, so in cooperative game theory, bargaining solutions deal with how players in a cooperative game can negotiate to reach a fair agreement. Okay. Um, the so there's something called the Nash bargaining solution. The Nash bargaining solution. Of course, now when you hear Nash, you're thinking equilibrium, right? So the Nash bargaining solution or the NBS, right? Um, the Nash bargaining solution or NBS is a popular solution concept which maximizes, in a game, everybody is looking for their optimum benefits, which maximizes. So whether they are cooperating or not, it is so people cooperate because because that's the best way they can get the best solution, right? So so the Nash bargaining solution is a popular solution concept which maximizes the product of the player's surpluses. Okay, surpluses are actually gains. Surpluses are gains over their disagreement points. Okay. So a very good example would be this. Imagine we have Nash. So let's talk about example of Nash bargaining solution. Okay. So consider two players. Consider two players, A and B, who are negotiating over the division of a total surplus of 10. Okay, maybe there's after all the agreement, so you don't have a surplus of say $10 million or $10 billion or 10 billion pounds or whatever, $10 billion. So consider two players A and B who are negotiating over the division of a total surplus of 10. You know, each player has a disagreement point. Each player has a disagreement point. Okay, that is the payoff they receive if no agreement is reached. If no agreement is reached. Okay, let's imagine that player A has a disagreement point of 2. And player B has a disagreement point of 3. Okay. So then we see that the total surplus to be divided is 10, and both players want to maximize their payoffs. Okay, so the Nash bargaining solution maximizes the product of their gains over their disagreement points. So I mean the disagreement points will now look like they are willing to let go of that, of whatever their disagreement point is. So whatever is left of what they have to share is what they will have to go with. So they want to maximize it. So the Nash bargaining solution maximizes the product of their gains over their disagreement points. Okay. So in that case, we have something like this. We want to maximize it's more like want to maximize XA minus 2. Okay, I guess we have come to that point where we need to change markers, right? Yeah, so we go for green now. So the deal is to maximize their profits over their disagreement point. So we have XA, the payoff for A, minus 2 being the A's disagreement point, and XB minus 3 being B's disagreement point 3. So, and that is subject to, so it's more like a linear, so not linear programming now, it's more like a maximization problem, an optimization problem, basically. So, and that is subject to the fact that XA plus XB is equal to 10, where XA and XB are the payoffs. Are the payoffs to players A and B, respectively. Okay, so we can say, okay, using the constraints, using the constraint, using the constraint, XA plus XB equals 10, we can express, we can express uh XB equals 10 minus XA. We can have this, right? And substitute and substitute. Okay, we can express that, right? And then, and substitute this, substitute this into the equation. So where we now have, okay, I think time for another switch over. So, and substitute into the equation, and then the new equation becomes maximize. Before it was XA minus 2, XB minus 3, but we have a new expression for XB. So we have XA minus 2. So instead of XB minus 3, now we have 10 minus XA minus 3. That's now XB minus 3. So now this is the same thing as XA minus 2 into 10 minus 3, that's 7 minus XA. All right. And then we can expand this. We have XA times 7, that is 7 XA. XA times XA, that's minus XA squared. Then minus 2 times 7, that's minus 14. Minus and minus is plus. 2 times XA, that's 2XA. That's 2XA, right? 2XA. 2XA. Then we now have 7XA plus 2XA. Okay, we can arrange in order of power, right? So we have minus XA squared, all right, plus 9XA minus 14. So that is the expression we have now. So it's more like want to maximize this thing now. So we can now go and say to maximize this quadratic expression, so we take the derivative, Of course, to maximize something, you differentiate and set to 0. Take the derivative with respect to XA, which is the payoff for player A, and set it equal to 0. So it means that we have d dxa into that expression. That's minus XA squared plus 9XA minus 14. Okay, and that is equal to 0, right? So we can differentiate with respect to, so differentiate minus XA squared, that's minus 2XA plus 9 minus 14, differentiate with minus 14, that's 0. This is equal to 0. So now we have 9 is equal to 2XA, okay? And then that means that 9 over 2 is equal to 2XA over 2. 2 cancels out. So we have XA to be equal to 9 over 2, meaning that XA is equal to 4.5. So that means the payoff that player A should get is 4.5 based on their disagreement point. So it should be 4.5. So player A should get 4.5. Now we need to get for B, right? Since we have got 4.5. So what we can do now is to substitute. So we can now substitute XA equals 4.5 into the constraint, which is XA plus XB equals 10. And in that case, we have XB equals 10 minus XA. That means that XB is equal to 10 minus 4.5. So XB is equal to 5.5. XB is 5.5. So with this, we have got the results we need. So we can say, thus, the Nash bargaining solution, is that player A receives 4.5 and player B receives 5.5. So you can say 4.5 plus 5.5 is 10. So with this now, we say the division maximizes the product of their surpluses. The product of their surpluses over their disagreement points. Over their disagreement points. All right, so with this, we come to the end of bargaining solutions in cooperative game theory. You see, like we said, in cooperative game theory, bargaining solutions deal with how players in a cooperative game can negotiate to reach a fair agreement. And we do this using the Nash bargaining solution, which is a popular solution concept, which maximizes the product of the players' surpluses. And their surplus is actually their gains over their disagreement points. So if they have to share 10, and each one has A has disagreement point of 2, and B has disagreement point of 3. So the product of their playoff minus their disagreement points, the product of the differences of their payoffs and their disagreement points, they will seek to maximize that, subject to the constraint that whatever their payoff should not exceed what they have to share. So, and with this, we have a bit of calculus in there, and then we arrive at this solution. So this is the end of bargaining solutions in cooperative game theory. Game theory still continues, so you want to tune in. If you have not signed up already, you want to do that right away so you don't forget. And of course, you need the notification bell so you can always get notified each time a new video is released. And then, of course, you want to comment. Let me know how helpful are these videos to you. And do you want me to solve a problem? Let me know. Do you want me to teach a topic? Feel free to also hint me. Then like and share so that more people can have access to this great content. Till I come your way again, keep playing the game of life with wisdom. Bye.